Hello, everyone. Welcome to the INNOQ Technology Day and to Daniel Westheide's talk, There and Back Again from Objects to Functions to Data. My name is Lena. I'm here as a moderator. You are welcome to write questions in the chat, just right beside of you. And after the lecture, we have time to answer some questions. Afterwards, there is still the possibility to switch to a fireside chat, in which there is the opportunity to ask Daniel some questions. So now have fun, and Daniel, you can start right now.
All right. Hello, and thanks for attending my talk today. My name is Daniel, and I would like to talk to you about this journey from objects to functions to data. And I'll explain more about what I actually mean with that in a minute. But first, let me quickly introduce myself. So I am a senior consultant at INNOQ, and I have been working there since 2013. I've often been in a position of mentoring or coaching other people in functional programming techniques. And one such place of mentoring was Scala Bridge, where I am the co-organizer of the Berlin chapter. But moreover, I also like to teach Scala and functional programming by writing about it. And by now I have actually written 3 books. And the last of them, Scala from Scratch Understanding, has just recently been released as a hardcover edition. And that book is part of a 2-book series, where the first one is obviously Scala from Scratch Exploration. And you can find more about how to get these books by following the link to my website. Okay. So when I was writing these last 2 books, I got quite a lot of great feedback from a couple of technical reviewers. And one of these reviewers offered a really interesting remark when he commented on one of my chapters, and it was this. I'm paraphrasing now, but I believe this is more or less what he said. He said that he had never realized before what a weird ride we take functional programming beginners on when we teach them this paradigm. So I think that most people come to Scala or also to other functional programming languages from years of experience with object-oriented programming. At least that's my experience from all the mentoring I've done. So the start of that journey is here, this peaceful, secluded and sedate area called the Shire, where people are serious about their traditions. They're used to using classes and subclasses and object composition everywhere, because this is how they have always done it in the Shire. This is what they know. And then they embark on their journey to the land of functional programming, where pure functions, currying, monads, and many other things await. And we tell them to stop doing what they're used to. They need to adapt to this new world. The journey will change them. We tell them that they can solve all of their problems they encounter with functions. With functions as values, which can be passed around and composed like any other object. And usually they will quickly learn to do that. So before you notice it, they are mapping, filtering, flat mapping, reducing, and so on, like a veteran functional programmer. But then comes the interesting point. some point in this process of teaching them functional programming, we tell them that they should stop using functions everywhere. So what we have been teaching them, what they thought was right, is suddenly wrong again. We explain to them that they should represent their program as data instead, and that they should build an interpreter for this data. And essentially in a language like Scala, this means that they are back again in the land of objects, classes and subclasses. I think that this journey that they set forth on is a really interesting one. But it's also quite a challenging one and probably scary. And it's particularly interesting because they may already be familiar with interpreters as a classic design pattern in object-oriented programming, right? So in this talk, I want to tell you a bit more about this interesting process of going back from functions to data. I want to talk about how we do it and why we want to do this. I'm doing this from the perspective of typed functional programming, using Scala for all of my code examples. But I think you don't have to be familiar with Scala to take something away from this talk. So if you're a novice functional programmer, for example, and you got a bit confused during this journey, my hope is that this talk will help you to understand the reasoning behind this journey from objects to functions to data. So let's start by examining why we do functional programming in the first place. Noel Welch wrote an excellent blog post about this, which is called What Functional Programming Is, What It Isn't, and Why It Matters. Now, he's done a really perfect job with his blog post, so I couldn't really describe it any better. I'm just trying to summarize the main points in the context of this talk. So essentially, pure functional programming helps us with two things. One of them is local reasoning, and the other is composition. But they're both really just two sides of the same coin. So what does it mean? Local reasoning means that we can reason about a single part of our program in isolation. Our understanding of what unit A does will not change when that unit is combined with another unit B. And because this understanding doesn't change, unit A can be composed with other units. And this is exactly how we manage to build an understanding of large code bases. Now, the smallest unit would be a function. Pure functions are functions that always return the same value for the same arguments and that don't have any side effect, like reading from a file, for example. And on this slide, you see two very simple examples of pure functions. One is a function called squared. So for the same integer value, it would always return the same value. Another is max, which expects two arguments of type int and returns a value of type int as well. And these functions are pure, like our mathematical functions. So we could easily see that we combine multiple of these functions together to form a bigger function. Which means, because these functions are pure, because we can reason about what they do locally, we can compose them. Now, impure functions, on the other hand, impede our ability to reason about a function. Two common scenarios are shared mutable state and talking to the outside world. If a function uses shared mutable state, then we cannot reason about it locally anymore. because it absolutely matters what other functions or modules do with that shared mutable state. And at the same time, we cannot compose that function with others anymore, at least not very easily. And on this slide, I changed the max function from earlier to take on a third argument, which is some shared mutable state of type high scores. It's a very contrived example, but I think it illustrates the point that now this alternative version of max is a function that we can't really reason about locally anymore, and we can't compose it anymore as easily. And of course the same is true for functions that talk to the outside world, like this random int function I'm showing you here. So every time such a function is called, it may return a different result. And that makes it quite difficult to reason about and to compose with other functions. Now in such a case, as functional programmers, what we want to do is to separate the description and the execution of effects. Here's an example. In the Scala Bridge workshops, we use a library called Doodle. And this library allows you to draw all kinds of shapes programmatically. For example, rectangles, circles, and so on. So let me just show you what this Doodle library looks like. So here I have a Scala worksheet with some Doodle code in it. And you see there is, for example, a function called rectangle. We call that function to create a black square and another square called a red square. So if we describe our program as data, which is what is happening here, it allows us to work with pure functions as long as possible. For example, we can actually call the fill color on a square, or we can combine multiple squares together, leading to this 2x2 value. And we are pushing the execution of effects away from the core of our program and delay it as long as possible. So if a function called rectangle would actually draw a rectangle, it would be quite difficult to compose this with other functions. But if it merely returns a description of a rectangle, then we can compose it with other functions that also return a rectangle with a different color, or that return two rectangles, or that transform a rectangle somehow. And it also means that we can reason about what these functions do locally. Now, separating the description and the execution means that we need to define data types for describing images. We will get to the topic of those data types shortly. For now, you can see here that this just returns data. So we have a value black square of type image, and it's actually an object of type fill color with certain fields, like an image and a color. And the same would be true for this 2x2 field, which is of type image, but it's actually an object of type above, containing a beside, containing a fill color, and so on. So in this talk, I would also like to show you how we implement such a separation of description and execution or interpretation in Scala. And then I will also talk about a few additional reasons for doing that, apart from reclaiming our ability to do local reasoning and to compose functions. But just to close off this part on Doodle, here we have actually composed a chessboard. And the point is that we haven't actually drawn any image yet. We have just data. And actually drawing that chessboard, that's completely separate from describing this image. So there is a method called draw, and only if we call this method, then this effect of drawing the image will happen. Okay, so this chessboard has been drawn to my other screen, but there you can see it, right? So this is our chessboard. All right, so let's move on. So let's say you work for a free mail provider and you want to support different ways to determine whether a mail is spam or not. Now maybe your solution will be based on a function of type email to Boolean, which I've done here in this example code. We have an inbox function which expects an email filter of type email to Boolean, among other things. So what you would do then is that you define a few functions of this type, which you can compose in quite an elegant way. For example, we have a function sent by one of, not sent by any of. We have a function minimum size, maximum size, and so on. So what we can do is we can combine these different email filter functions in interesting ways. And some of them I have defined here in this predicates object. So we can, for example, negate a filter, or actually we can negate any function from type A to Boolean. And email filter would just be an example of that, email to Boolean. We have another function called any, which expects one or more predicates and returns a predicate A to Boolean that is true if at least one of them is true, and so on. So this will certainly work, but we can ask ourselves, do we really need this freedom? Do we need the ability to pass in arbitrary functions of type email to Boolean? Because the truth is that our program only supports a very small subset of all these filtering predicates you could imagine. But since these supported filtering predicates are represented as functions, the actual behavior is completely opaque to us, right? Let me demonstrate this in another worksheet. So I can use these predicates, for example, and say I want to negate a predicate which expects an email and returns a Boolean. I want to negate this one. So what I get back here is just some Java or JVM lambda, right? So we don't know anything about what this function does. So maybe something less powerful would be good enough. Or maybe we could even benefit from a less powerful approach that doesn't give you as much freedom to create arbitrary email filters. So what happens if we turn the small set of supported filtering predicates into data types? Well, in typed functional programming, when we want to represent a program as data, we define algebraic data types. An algebraic data type can be either a sum type or a product type. A sum type defines a set of alternatives. So something is either an A or a B. A product type is composed of multiple types. For example, a type C might be defined as A and B. Now in our example, we will define a sum type where each alternative represents one of the predicates that we support. So this is in a file called mailfilter.scala. So what you see here is the algebra of our program. And in Scala, algebraic data types are represented using subtyping. But this is actually just an implementation detail of the language. So we have a sealed trait mail filter, which means we know at compile time that the only subclasses that exist are the ones in this file. And then we have a bunch of case classes that are subclasses of mail filter. One for minimum size, one for maximum size, one for send by one-off, and so on. But what this means is that now we are kind of back again where we started our journey in the world of classes and subclasses. And now we can describe our default filter using pure data. So here we define a default mail filter, and instead of using or calling the functions, we actually need to use the constructors of our case classes. So we create an any, which contains a vector containing a send by one-off and an every, and so on. So now our default mail filter, or actually any mail filter, is pure data. There's actually no behavior to it yet. It's common to provide a domain-specific language, which makes it a bit nicer to create our programs. So what we can do, oh, this is the wrong package. What we can do is all right, let's have a look. Okay, here's a package object I wanted to show you. So what we've done here is that we have created functions, or actually methods, which are factory methods or factory functions, and it's one function for each case class, so for each alternative of our algebraic data type mail filter. Now this is a bit of boilerplate to write this stuff, but now it becomes a bit nicer to use our algebraic data type if we want to create a mail filter. So now our default filter can be created just as before, when we had only ordinary functions. So this code creating the mail filter looks exactly the same as when we had functions and no data types for describing a mail filter, right? And here's another example of that filter. Now, I already said that our mail filter is now pure data. So the thing is that right now, nothing happens if we merely describe a mail filter. We need to interpret it somehow. And I'm showing you an example interpreter right now. So here we have inbox, and it receives an email filter and the mails. This is the same as before. And then we need to apply this filter. And for that, in this example, I'm using a straightforward interpreter which actually transforms a mail filter into a function of type email to Boolean. So I'm using pattern matching here on our algebraic data type to derive a corresponding function from each of them. And then we use that function to filter an in-memory sequence of emails. Now, when the program you describe actually consists of a sequence of steps that depend on previous steps, typed functional programming often uses a more formalized approach, which is called free monads. However, this is really a bit out of scope for this talk, and I want to focus on the idea of separating description and execution instead of doing a deep dive into specific techniques. So, one benefit of having the description decoupled from the execution is this. Now we are free to implement additional interpreters, and they can interpret the same data just in a different way, right? So for example, maybe we want to perform this whole mail filtering in a database instead. So a second interpreter could use the mail filter description and turn it into an appropriate SQL query and execute that query. So apart from this advantage of delaying effects, supporting different interpretations is another important motivation for representing your program as data. But there are other reasons as well. If our program is just data, one interesting consequence is that we can inspect it and we can transform it. Let me show you another example. So here in this filter, you see a program that contains nested occurrences of every and any. And this nesting is actually completely useless. It won't have any effect. So because our program, our mail filter, is just data, we can actually normalize such a program by removing nested occurrences of every and any. So let's see if we can do that. I have the optimizing pure mail, which is just another interpreter, and it has a function called normalize. And now I'll give it the filter here. So what we get back here is a normalized version of the mail filter we put into the normalize function. It consists of an every with filters minimum size, maximum size, any. And the original filter, we can also have a look again here. No, we can't. Let me put that into another line. But you already saw it previously. This filter has all these nested everys and any's, right? So this kind of transformation or optimization would absolutely not be possible if our program consisted just of opaque function values. But there are even more benefits to going from opaque functions to data. So if our male filter logic is just data, it becomes relatively straightforward to serialize it. So while it is possible to also serialize arbitrary functions, it's often slow and dangerous. I mean, just think of the Java serialization mechanism. So if we can easily serialize our program, we can store it in a database, for example. So each user can have their custom spam filter configuration persisted in the database. And from there we can load it and deserialize it without any danger. And maybe just as interesting, because it's data, we can also show the user their spam filter configuration, because this data can be inspected. But the user will have a hard time inspecting their own mail filter configuration if it was just a bunch of composed opaque functions. And finally, if we have data instead of functions, it makes it a lot easier to distribute work in a cluster. Today, it's still pretty common to send arbitrary functions around when doing distributed computing, if you think of frameworks like Apache Spark, for example. So what if we were instead sending program descriptions as serialized data around? So we could probably serialize them using an efficient binary format like protobuf, or even in human readable form as JSON. And this would be a lot safer and maybe even more efficient than sending arbitrary code around between the nodes in a compute cluster. And this process of going from functions to data has a name. It's known as defunctionalization. And if you want to read more about that, there is a great blog post by James Koppel about it, which I have linked on this slide. So, that's it. I hope you have a better idea now of the reasoning behind this strange learning path, which first goes from objects and classes to functions everywhere, and then tells you not to use functions everywhere, because there are certain use cases where it's actually a better choice to have data instead of functions, which is kind of a way back to classes and objects, at least in Scala, where algebraic data types are represented as classes with subclasses. So thank you very much for watching, and I'm looking forward to answering your questions.
Thanks, Daniel. Thank you very much. And now you have the opportunity, so the listeners have the opportunity to ask Daniel some questions about his talk. You can just write them in the chat window to the right of the stream. So I hear some, I can see some nice words. No questions so far.
Yeah, feel free also to just go to the fireside chat later.
Yeah,
if you want to ask your questions, not via chat, but if you actually want to talk to me.
Yeah. So that starts 15:30 or 15:35. So there you have the possibility to speak to Daniel in person. So since I see one comment.
Okay, that's not really a question.
It's more a
but we can surely discuss that in the fireside chat later.
Okay. So I think since we have no actual questions in the chat, I'd say we stop this session here right now. And yeah, we're looking forward to see you in the fireside chat.
Yeah, thanks for attending the talk. And I think the fireside session will only... Oh, there is one question now. So are there cases where you would suggest to stick to functions or even objects? Okay. So the point of my talk was, of course, not to say you should never ever use functions again, so that once you have learned about using data to represent your program, that you should never use functions. So I would only use this data-driven approach if there is a use case for that. So I wouldn't actually do it the other way around. And one use case for using data to describe your program is if you actually need multiple interpreters, for example, or if you have a need to inspect this program as data or to persist it and load it again. If that's not the case, I think sticking to functions is usually a good approach. So I hope that answers the question. And if not, we can, of course, talk about it more in the fireside chat. So
should we post the link from the fireside chat?
Oh yeah, please, if you have it at hand.
Yeah, I have it. Wait a second. So this is the link. Actually, I hope it is the link. No, this is not a link. So I think this is not possible.
Oh, you can't send the link?
I don't think so.
Okay, but it's actually just the next session in the program.
Yeah. But it's
Oh, it's not a link, yeah.
No, it's not a link.
Okay, I think there was one further question and we still have a few minutes, right?
Yeah.
Where was it? Here. I guess if there's a default interpretation of my data, coupling it to the data is fine. Compare that to making use of polymorphism and the visitor pattern in object-oriented program. Yes, exactly. So as I already said, this approach that I describe here towards the end of the talk is really, you have a big advantage of it if you need multiple interpreters. And if that's not the case, then the approach you described should work just fine. Okay.
Okay.
Let's wait if there are more questions, maybe of 30 seconds or so. And if not, then we can close this session. And yeah, I wanted to say that the fireside session, I think it starts at 3:30, right?
35.
35.
Yeah.
Okay. So you may have to wait a few minutes between these two sessions.
And it's just possible to enter this session just a few minutes before 3:35. Yeah.
Okay. So Torsten wrote that we can actually move over there a bit earlier. That's great. There was one other question. Would you ever consider using object-oriented programming over functional programming? I'm not sure, at least not in the traditional sense of object-oriented programming, or the one that has become popular using languages like Java. I have actually been using actor-based architectures quite a lot, and this is actually much more what the inventors of object-oriented programming had in mind. So yeah, I think there is a use case for that. But you can actually combine it with functional programming, because inside of a single actor you can use functional programming techniques and immutability very nicely. Okay, maybe we should just move over to the fireside chat.
Yeah.
So thanks again for watching. Thanks for all your questions, and I'm looking forward to discussing a bit more with you in a few minutes.
Okay, see you there.
See you.
Bye.